Hello, my name is Muhammad. Today I'm going to be presenting the section Metalinguistic Abstraction from the book Structural Interpretation of Programs. Sorry. For this section, I'm not going to try and present a coherent stream of ideas that's going to lead us to the core idea. I'm going to approach this differently by just giving the core idea outright and just guiding the user about how to do this at home, because I think this is a very important section, and however much I try, I'm not going to do it justice by trying to break it down into simple ideas and presenting them in a coherent fashion. So I'm just going to present the idea as is. The general idea is that when you are inside a system and you find yourself limited, you have to realize truly limited. I mean, it's not the limitation does not come from your skill or from motivation. It comes from it's mathematically proven that you are limited. This means that the system is the problem, and in this case, when you are interested in abstracting in order to get to your goal, then the problem is no longer how to find ways to abstract within the system. You have to get out of the system and find ways to abstract the system itself. In the case of computation, this mainly deals with interpreters, and the idea is that if a language limits how you can think, this is how language can kind of limit you, then you have to build a new language. This is the core idea. This is the presentation. If you have just come from watching my previous presentation, and you're expecting a motivation, you're expecting a context, and then we kind of present the history of sorts, how we got to the core idea. I'm not doing this today. This is the first slide, and this is the core idea of this section. A language is going to limit how you can think. And then what you have interest in is to build new language, to abstract the system itself, rather than trying to find new ways of abstraction within the system. For the core realization, which is that interpreters are programmed and languages are also programmed, it does not come from these two ideas. This is just a realization that you are going to come across as you grapple with this idea. I'm just writing it here to kind of highlight its importance, because this is, once again, for this presentation, this slide is the main slide. So let's kind of move forward. Obviously, to present the limits or how language can kind of limit you it's going to limit you by defining your mode of thinking, and language does this. General idea is that language does this by embedding assumptions into itself. But to kind of give an example, or to give a hint, is that languages by definition define your tools to talk to with the computer, and by defining the tools they kind of define your set of possible action. It defines your ways, the ways you can think, you can communicate with the computer, and this by definition kind of limits your mode of thinking. And it does this by defining meaning of abstract concepts, abstracting the term of computer science, things like state or procedure. And these assumptions can be helpful. They can streamline processes because they kind of make things easy, but they can also be harmful when they constrain the solution space. This is a nice way to say it. A language can define your mode of thinking by constraining your solution space. So it can also limit you in terms of implementation stuff, but I'm not like how the amount of code you can write, but I'm talking more so about the solution space, about how you before you even start writing code, you are trying to think conceptually about your problem. The language is going to define how you are going to think about the problem. This is a very key idea. So let's move forward. As for interpreters, once again, I have already presented the main idea, which is that if you are limited within a language, you no longer need to find new ways of abstraction within that language. You have to find a new language. You have to define a new language. So the idea I've already presented. I'm just going through certain ideas to kind of give you hints as where you can go and find this issue yourself. I believe this is the best way to present this section of the book. So for interpreters, the main idea is that they take in a language as a form of input, and they interpret the language. And the key idea of how they interpret the language is they have evaluation rules. Languages themselves have to follow a certain protocol to be designed. They need the grammar, they need also evaluation rules within themselves, and the interpreter kind of defines the evaluation rules. And the key idea here is that these evaluation rules kind of propose or kind of make each language as a theory of computation, because once again the language is kind of defines your set of possible solutions, and it defines your set of possible solutions in a conceptual way, so you have to think about problems in a certain way. So it's a form of theory of computation. Each language is a blueprint about how to try and compute. And there you can also think about it in terms of high-level languages and low-level languages. This is what I'm trying to say here by the boundary between user and machine. Think of it about things like C, where you can define, you can have more access to the variables and what type of stores they have, and something like JavaScript, where you can just say var and it kind of infers the type itself. And you can go even further and think about assembly, and you can even go further and think about word computation languages, things like brainfuck, if you ever heard about this one. And when you're trying to grapple about the idea of what about languages, you can also try to answer key questions that are going to help you understand the concept. These are useful for tactical stuff, so you kind of understand what lazy evaluation non-determinism is. But the main idea is to try and figure out where does the loop end. Because once again, interpreters are programs and computation models at the same time. So who depends on who? Like where does the loop end? Well, the idea is that there is no bottom layer. It's not, as it's implied, it's a loop. It's a circle. It is kind of circulates, and each section of the loop or each layer kind of presents possibilities for abstraction. So procedures, the abstract computation. States, abstract time. This is what we studied in the previous chapters, and interpreters, abstract meaning. But if you remember, in the previous chapters we were trying to kind of always to introduce meaning into program design, so that when you design a program, it reads like natural language. It does not read like code. Like it reads like something you can understand. Well, interpreters kind of define meaning in a sense because they define your solution space, and this is what I believe makes interpreters the ultimate power, because the ultimate abstraction is to control the interpreters, because they define the space of thought. This is important. This is a quote. This is not mine. I got this from another book, and it says that mathematics studies structure, programming builds machines, and metalinguistic abstraction designs universes. This is, I think, it's a very, very nice way to put it, because when you have a problem, and the average computer scientist is going to try and solve the problem, but nobody thinks about the tools you have, because the tools you have are going to define how you think about the problem. Obviously, if you are a computer scientist, you're not going to at each problem try and design into language to work with the problem. This is not feasible. This is what high-level firms do. For example, and I'm not going to cite examples, but this is what they do for each problem. They don't define their languages, but they define their own framework, which kind of things like React. This is how React was born, for example. It was designed as a form of as a framework built on JavaScript to kind of streamline the process of computation in that sense, and it kind of became popular because it was very useful and it was general. But they do this for many other projects. And this kind of gives you a hint that in order to solve problems, real problems, not common problems, because most computer scientists just spend their time doing or software engineers spend their time solving common problems, things like build a website, implement this feature, this, that. But if you are truly trying to harness the machine, because I firmly believe that a computer scientist, his role in the supply chain, if you mean, is to kind of be the link, because if you want to do science, you need a brain. And a computer is just a very efficient brain, but it's a stupid brain. It's a very powerful brain, but you kind of need to know how to harness it. And a computer scientist is a specialist at harnessing the power of the brain. And before you even try to harness the computation power of the brain, you have to define the language. This is key. This is because this is how computer scientists should work. You have a problem, a real world problem that you want to solve. You can try to solve it with your own brain, but that's going to take a lot of time, probably not possible for many of the problems that we are going to face at this current level of civilization. So you need a computer, or potentially in the future a much more powerful computation machine, whatever it is. And before you even start to talk with this machine, you have to define the talking terms. This is the key. This is how you can understand why interpreters are so important. And obviously you do that by designing new language with new evaluation rules, with a new grammar. This is the key idea of the chapter, as I said. If a language limits how you can think, you build a new language. This is general advice, but as I said, when you're trying to tell a computer how to, or communicate with the computer about how to solve a problem, it is much more useful to define the language, to define the possible sets of problems, and to define the method of thinking. And I don't think I did a good job of explaining, but I think the idea got through. So thank you for listening.